So welcome back. In this second video, we'll continue discussing Markov chains, and now we're going to talk about the mini-forward algorithm, and also we're going to talk about stationary distributions later on. So the mini-forward algorithm is a very simple idea. We want to simulate the chain. We want to compute the probability of x for a sequence of days until we reach a certain day t. So we need to compute this probability. Let's suppose that the initial probability is null, right? It doesn't need to be a deterministic value. It doesn't need to know that it's sunny or rainy day. We can say that the probability of x1 is something like possibly 0.5 and 0.5. So on top, let's say that's sun, and on the bottom, I'm going to say that is rain, right? So we can put any probability distribution that we want for x1. And starting from x1, I want to compute x2 and x3 and x4 and continue doing that until xt. So how do we compute that? So actually it's very simple. We want to know what is the probability of xt for a certain t. We will compute that from xt minus 1. So we're going to compute xt minus 1, and from xt minus 1 we're going to apply the transitional probabilities and compute the xt. So you're going to make a chain, right? So if I want to compute if t is equal 5, I will need to compute first x2, then x3, then x4, and from x4 I will compute x5. So let's first think about how we can compute the probability of xt from xt minus 1. So this probability of xt, we need to introduce the variable xt minus 1. And the way that you do that is by using the case analysis. So remember from our lecture about probabilities that we saw that we have this tricky, and it's very useful. I can say that the probability of xt is equal to the sum for all possible values of xt minus 1, the joint probability between xt and xt minus 1, right? So we can think that is like the opposite of doing the marginalization. That's an operation that we are used to already. If you think from right to left, it's like doing the marginalization. We are summing one variable and eliminating it. So in this case, I'm doing the opposite operation. I'm introducing a new variable by summing this variable for all possible values of the xt minus 1. And given this joint probability here of xt and xt minus 1, what I can do is to apply the base conditioning and transform this to a conditional probability. And that's give us this expression here. So it's going to be the sum for all possible values of xt minus 1 of the transition probability of the probability of xt given that I was in the state xt minus 1 times the probability of xt minus 1. So let's try to think a little bit about this and see if we can understand this. I'm going to write here in the corner to try not to use too much space, but thinking about it, just two possible states, sun and rain. So we want to compute this, the probability of xt equals sun, right? So we wanted this quantity here, and this is going to be a sum from two possible terms. The first term is that in the past, in the previous time xt minus 1, I was in a sunny state already. So it was already sunny in the previous state. And from here to here, I needed to stay in the same state. So it's going to be the probability, the transitioning from sun to sun, right? So basically what I'm saying is that this guy here is going to be a sum. So this guy here in the middle, the probability of xt equals sun, is going to be the sum of two terms. The first term, in the previous state, I was already in a sunny day, and I transitioned from a sunny day to a sunny day. So we have this transition here. So I will multiply these two guys here, this guy and this guy here, and it's going to be my first component. The other possibility is that in the previous day, in t-1, it was a rainy day. So the previous day was a rainy day. So in this case, I will take this probability and multiply by the transition probability of having a sunny day, given that yesterday was a rainy day. So this is going to be my transition. So we will transition from rain to sun. So these are the two possibilities of being a sunny day today, right? Yesterday was sunny and continues to be sunny, and yesterday was rainy day, and I switched from a rainy to sunny day. So basically, that is what is written in this equation here. Okay, let's take a look at one numerical example. We have this transition probability here, and we are simulating the chain for these four time steps. So what does it mean to have those numbers? So let's suppose that in the first day, there's going to be sun, there's going to be rain. In the first day, I'm sure it was a sunny day, and I want to know what's going to happen tomorrow and the day after tomorrow, and continue that in this sequence. So how do I justify this number here, 0.9? Where does it come from, right? It comes from the following. In the previous day, I knew that I had a sunny day times what is the probability of transitioning from a sunny day to a sunny day is going to be this guy here, 0.9, plus what's the probability of in the previous day to be a rainy day, 0, times what's the probability of transitioning from rainy to a sunny day. It's going to be this guy here, 0.3. That is the 0.9. And how do I justify this 0.1 here? So it's going to be the probability of, let's just me erase this, the probability of yesterday it was a sunny day, and in fact it was a sunny day, times the probability of transitioning from a sunny day to a rainy day, that is 0.1, plus the probability that yesterday was a rainy day times this the transitioning from rainy to rainy, that is 0.7. So that's going to be 0.1. Okay, makes sense. And if you want to justify the next one, so let's write here on the top. Let's see if we can do at least one of those. So how I justify this 0.84 here? So yeah, yesterday it was a sunny day. So yesterday, so now the yesterday changed, right? Because yesterday is now x2 because we are computing for x3. So yesterday was x2. So yesterday it was a sunny day, 0.9 times the probability of, just erase this, the probability of staying in a sunny day, 0.9, plus the probability of a rainy day, 0.1, times the probability of transitioning from a rainy day to a sunny day, 0.3. So it's going to be 0.81 plus 0.03 equals to 0.84. Good. And this 0.16 here, how do I justify this? Again, it's the same thing. Yesterday was a sunny day, and I transitioned from a sunny day to a rainy day, 0.1, plus yesterday was a rainy day, 0.1, times the probability of staying in a rainy day, 0.7. So it's going to be 0.09 plus 0.07 equals to 0.16. Okay, so what we can learn from here, we can see that given these transition probabilities, that I was completely sure about what was the weather today. So it was a sunny day, but as the time passes and we transition from one state to the other, our uncertainty increases, right? So I become more and more uncertain about what is the weather for the days that will come. So tomorrow I can predict with a little bit more confident, but in 2 days ahead I will be less, and 3 days less and less confident. So the uncertainty increases as the time passes. So we can better formalize what we discussed in the previous slide into an algorithm, and we call this the mean forward algorithm. So we're going to specify as input the time n, so we're going to simulate the chain for n time steps, the transition probabilities, and the initial probability distribution, the prior for x1. I'm going to output, there is a mistake here, so it's going to be the probability of xn. So what we do is to first initialize this array here, so it's going to be a matrix, then I'm going to store the values that we compute. So it's something like a table where we have all the possible time steps, starting with t equal 1 and t equal 2 and t equal 3, and it continues. And here we have all the possible states. So we have one row for each possible state, assuming that we have more than 2 states here in this example. So we initialize here for t equal 1 with the prime probabilities for each state, and we simulate the chain for the remaining time steps. So our algorithm is very simple. We initialize the values in one specific column t with 0, and we accumulate the sum, and this is basically the equation that we had in the previous slide. So we're going to look for all possible previous states xt minus 1, and I'm going to accumulate the probability of being in that state times the probability of switching from the state to the state that we are specifying at xt. So we're going to sum this, and at the end I will return the probability of x and n. So it's going to be the probability of x at the time n. That is what we are looking for. If we think about what is the complexity of this algorithm, it's very clear that the time complexity will be dictated by these 3 for loops that we have here, here, and here, right? So this first one depends on n. That's why we have this term here, and these 2 internal for loops, they depend on the number of states. That's why we have this a number of elements in x squared. So this is another example, just to check if you were understand everything correctly. So this is the grasshopper example. So imagine that we have a grasshopper, and it can jump to the left or to the right, and it has those probabilities here for jumping. So if it is, for instance, in this initial position here 0, it can jump to the left with 0.5 probability, it can jump to the right with 0.5 probability, or it can stay in the same place with 0.5 probability. And that's continuous until it reaches the border, and when it reaches the border like this one, it has the probability of 0.75, that's going to be the sum of these two to continue in the same position, or a probability of 0.25 to come back to the position that it came from. So this is going to be the transition probabilities expressed here in this graph, and we can compute what's going to be the states, the probability of the states over time. So it's going to be the mean forward algorithm. So let's suppose that in our initial state, the probability of x1, we know that the grasshopper was in the central position here. So what can happen from here? So this is our initial probability distribution, our priors. When we have one time step, our uncertainty is going to increase because we not be sure anymore about the location of the grasshopper. So what can happen? It can stay in the same place. So it's here, right? So in the 0 position, it can stay in the same position. So it's going to be 0.5, or it can jump. It can jump to the left or jump to the right. So if it jumps to the left, it's going to be like this, 0.25, or if it jumps to the right, it's going to be 0.25. That is expressed here. If we have 2 time steps, it's going to be a little bit more complicated. We have to consider all possible states. So let's suppose that we are in this position here. So let's compute for this entry here. How much is going to be? So there are actually 3 possibilities. The first one is that we are in the position 0 in the previous state, and we will continue in the same position. So it's going to be 0.5, that is this probability, times the probability of transitioning from this position 0, from the position 0 to the position 0. That's going to be another 0.5. So it's going to be 0.5 squared. And we also have 2 possibilities. I was here, so the grasshopper was here, and it decided to come to the right. So it's going to be 0.25 times the transition probability of moving from -1 to 0, that is 0.25. The other possibility is it was here, and it decided to jump to the left from the position 1 to the position 0. So the previous probability was 0.25, and the transition probability is also 0.25. So it's going to be 2 times 0.25 squared. So we computed that, it's going to be 0.375. We can also compute to another position, right? So let's suppose that we want to compute to this position here. So what are the possibilities? Well, the first possibility is that the grasshopper was already here, and it decided to continue here. So it's going to be 0.25 times 0.5. 0.25 is the probability of being in the previous state, and 0.5 is the probability of continuing here in the state -1. Another possibility is it was actually here and decided to jump to the left. So this is 0.5 that we have here times the transition probability, that is 0.25. There is a point here. So it's going to be 2 times 0.5 times 0.25, that's equal to 0.25. If you want to compute it for this guy here, there is only one possibility, that is, well, it was here in the position -1 and decided to jump to the left. It's going to be 0.25, that's probability of being in the position -1 and jumping to the left, that is another 0.25. So I'm doing this transition here, and they're going to be 0.25 squared, that's going to be 0.0625, and they're going to be symmetric to this side here. So what we can think is that we can organize those numbers here that we have into a transition probability T that we have already discussed in the previous video. So this is basically the transition probabilities organized in the form of a matrix. So we're going to put xt-1 here and xt here. So it's going to be the probability of xt given xt-1. And we can face all those computations as a multiplication between the vector and a matrix. So we can have this, it's going to be the initial state. I'm going to multiply by this matrix here, and we'll get this guy here that corresponds to this probability of x2. And we can take the probability of x2 again and feed here and multiply by the transitional matrix, and I'm going to get the probability of x3. And we can continue doing that. So we can express like this: the probability of xt is going to be multiplication between this guy here, that is a vector that represents the probability of each state, times this transition probability, I will call it T instead of D, the transition probability that is this guy here in the middle. So one interesting question is that what happens if we apply this mini-forward algorithm for a very large number of time steps? And it's interesting to note that we will get into what we call a stationary distribution. So considering these transition probabilities here, right, let's suppose that we start in a sunny day. So this is sun, this is rain. So we start in a sunny day, and we're starting simulating the chain, and we're going to see that it changes to 0.9 to 0.1. So we start increasing our uncertainty, but if we simulate, we get into this stationary distribution, 0.75 and 0.25. And if we continue simulating, it will not change. It will continue to be 0.75 and 0.25 eternally, right? That's what we call the stationary distribution. We get into this position and never changes. And what happens if we change the input, right? So is this stationary distribution sensitive to the initial conditions? For these specific transition probabilities, it's not. We can specify that we're going to start in a rainy day, and I'm going to see that it's starting to change, increasing our uncertainty, and we end with the same stationary distribution. For this example, it doesn't matter. We can start with any probability P, and 1 means P for the sun and rainy days, and we will end with exactly the same probability distribution. So it's interesting to note that the initial probability distribution has less and less effect over the chain as the time passes, and we end up converging to a stationary distribution that is independent of the initial distribution. That's going to happen for most of the chains. So we can formalize this idea a little better. So we can say that the stationary distribution, that is the probability of the state X, if we simulate the mini-forward algorithm for an infinite number of time steps, will be equal to the probability of the next step. So going to be infinity plus 1. So basically, that's what we call in the convergence, right? So it converges to a single stationary distribution, and it will not change anymore from that position. And we can extend this guy here using the equation that we use to define the mini-forward algorithm. So it's going to be the probability of the p to the time infinity of x multiplied by the transitional probability. So as we have the p of infinity here and the p of infinity here, we can say that I will change this notation a little bit because it's more common to call this the pi. So use the symbol pi to denote the stationary distribution for Markov chains. So pi of x is going to be equal to our definition of the mini-forward algorithm. So I'm going to apply the transition probability to the pi x, and you continue to be the same probability distribution. So we got into stationary distribution, we got the convergence. And we can also express this as a multiplication of a vector to the transition matrix. So it's going to be pi that represents the vector, going to be equal to pi times the transition matrix T. So one relevant question here is how do we compute the stationary distribution? And it actually is very simple to do that. So we make use of the definition that we had before. So it's going to be like this. The probability of x is basically the idea that we had of the mini-forward algorithm. But now making use of the idea that the stationary distribution never changes once we have reached it. And we make a small system of linear equations here. So we're going to state that the pi, that's the stationary distribution for sun, is going to be the sum of being in the stationary distribution and transitioning from sun to sun. So I was in sun and continue to be in sun, plus the probability that I was in rain and I'm transitioning from rain to sun. The second possibility is the probability of rain. So it's going to be the stationary probability of rain means that it was in a sunny state and a transitioning from sun to rain, plus I was in a rainy state and a transitioning from rain to rain. And we know how much are these because we can find here in this graph that represents the transitional probabilities. So the probability of given sun is going to be this guy here, 0.9. The probability of some given rain is going to be this guy here, so 0.3, and I specify all the values. So once I have this, I will simplify. So from here it's a simple simplification. So I discover that pi of sun equals to 3 pi of rain, and pi of rain is going to be 1/3 of pi of sun. And there are many values that we can replace here, so we satisfy these two linear equations here, but we make use of this condition here. So we know that these are probabilities and they must sum to 1. So the pi of sun plus pi of rain is going to be equal to 1. And if we use this, we get into this. That's the stationary distribution for this example. Okay, so I think that is a good moment for us to make a break, and we'll continue in the next video discussing more about the stationary distributions. See you soon.